space engineering. And today we will discuss the new topic. Before we will start, just one comment. One comment regarding to what? Regarding to the previous topic and practical calculation of the initial data on previous topic. It is not correct to exclude some experimental points from the analysis when we make the first task, when we construct the model, Watson-Miller model for the long-term strengths. It will be not correct to exclude some experimental point, some reference data from the analysis, because it is material, and of course it is clear that we try to combine all of the possible states of material. I mean, strengths of material under different temperatures and different loading time. We try to combine by one single model. And of course, it will be not possible that some spline, some curve will cross through the all points at the same time. Some points, of course, will be crossed by the curve, but some one will not, and the deviation of the reference data from the curve that we try to draw through the points. This is the accuracy of our model. This is like a characteristic of our model, a characteristic of the accuracy of the model which we try to construct. And the better matching of the curve, proposed curve, with the reference data, reference point, of course, it shows or represents the high accuracy model, corresponds with higher accuracy model. But unfortunately, it cannot be obtained the same accuracy for the all reference data, all reference points. As an alternative, we already also described with you previous time, as alternative, we can use the another model, which called like long-term strength curves. Long-term or curves of the long-term strength. And the main difference between the long-term strength curves and Larson-Miller model, the main difference between them is what? That the Larson-Miller model should be constructed for the entire set of the reference data, the reference point. But long-term strength curves should be constructed only for the set of the point that corresponds with constant temperature. Different time to fraction, but constant temperature. And in this case, of course, the curve which we draw through the reference points, through the set, some set of the reference points, it will be much better. So I hope it's clear that it's not correct to exclude the experimental data, some experimental data, just exclude from the analysis, from the constructing of the model, because it will change the resulting curve when we will draw it through the set of the points And if we will exclude some points from this process, in result, we will get the another curve with another parameters, and it will go not at the same manner as if we will describe all of the reference point together simultaneously when we construct the model of Larson mirror for the long-term span. I hope it's clear, and you will not do the same. You will not make the same mistakes anymore in further analysis. If we should approximate the reference data by single curve, by applying the common law, common common model. And if we want to represent the entire range of the reference curves, of the reference points, reference experimental points, experimental data, entire set of the experimental data by one single model, we should describe all of the points which we can find in the reference literature, reference book or material. Another case, when we process the experimental data, not reference from the book, but experimental data, when we provide experiment, we repeat the experiment with the same settings several times, and then we process the results because it is a statistical result, and we should make some average. We should get some average value from the each set of operational conditions. And in this case, of course, some experiment can go wrong. We can make due to wrong measurement, due to the fault of the gauges. Doesn't matter. Any reason can lead to the wrong data, and of course, in this case, we should exclude the wrong data. But if we already use the reference data from the reference literature on material, reference book on material, so it is already cannot be excluded. It is already as is. I hope it's clear. Well, what we will talk in today about. Today we will describe such issue like relaxation of the stress state in the material caused by the creep of the material. And to describe this issue or problem, we need to talk a little about what is the stress relaxation, under which operational conditions it can appear, and what is the creep of material. So let's go step by step through these questions. First, stress relaxation. We have some structure, and the structure under the operational conditions will be loaded, and loads can be different. It can be thermal load and power load. Thermal load is on. Thermal load, sorry. Thermal load, I think it's already clear. This is heating of the structural components by the ambient, which is around of part which we have described, which in operational conditions. And let's describe, for example, components of the engine. In engine, we have the main units of the compressor, combustion chamber, and turbine. And let's talk about compressor or turbine. Both of these units consist of stator and rotor components. Stator are not movable and they represented by casing and stator vanes, non-moved vanes, and the rotor represented by what? By set of the rotor blades, discs, and shaft. Well, if we will talk about compressor, the compressor disc. Let's divide on the group the blades and disc. Disc is loaded by what? Is loaded primarily by the centrifugal force, and centrifugal force leads to tension of the disc. Tension in two directions, in radial direction, and due to deformation, we have also tension in circumferential direction. Generally, disk is loaded by tension. What we can say about the bending, about the loss caused by the flow, gas loss, let's say gas loss. The design of the discs, design of the rotor. If we will talk only about this, it's made in such a way to ensure the enough rigidity, enough stiffness to prevent high level of the bending or in discs, in compressor discs, for example, because the compressor discs have a thin wall, they're not thick, they're thin. And the design of the disc, design of the rotor is that to prevent the bending of the disc, high level of bend. So we can say that the discs of the compressor, all of the discs of the compressor are designed in such way to be loaded only by the centrifugal force due to rotation, and they are not loaded by the gaseous load. Even now, I guess you have a course project together with Professor Bezugli and Professor Garkusha, am I right? And in this course project, you have calculate the strengths of the blade, strengths of the disc, and frequency of the blade, initial frequency of the blade. And if you already make calculation, prepare calculations of the disc stress state, you just pay attention on the type of load. In such calculations, simplified calculations, you will not describe the bending, some bending caused by the gaseous force, by pressure difference, which acts on the left and right side of the disc, which is negligible. Because of the stress caused by such type of load is very, very, very small and can be excluded from anatomy. So when you will perform calculation of the disc in your course project, you will take into account only the rotation that leads to generating of centrifugal force and corresponding tension stresses in radial and circumferential direction. And you also will take into account the thermal state of the disc, the temperature difference along the radius, which also will lead to additional deformation and corresponding stresses, thermal stress. But should be taken into account only for the, if we talk about compressor disc, for the intermediate stages and higher number of stage next after downstream stages. So intermediate, the last stages of the compressor. And of course, for the turbine disk. Turbine disk also is loaded only by centrifugal force and temperature difference. Thermal gradient that leads to additional deformation, thermal deformation, and corresponding thermal effects. What about the blades of the compressor and turbine? Blades are loaded, all of them are loaded also due to rotation. I talk about the rotor blades. They loaded by the centrifugal force, which causes the tension of the blades. In addition, the blades are operates in the gas flow, in the working fluid, gas flow or air flow, depends on what we describe, compressor or turbine. And of course, the pressure difference on the blade airfoil will lead to the bending of the blade, especially for the compressor blade, because the compressor blade is very thin. It can be represented just like a curvative skin, curvative surfaces, just with the variable thickness. And the mass of the compressor blade is not so high to generate extremely high stress caused by the centrifugal force. So stress caused by centrifugal force is much higher, much lower for the compressor blade than for turbine because of the much lighter. The airflow of the compressor blade is much lighter compared with the turbine blade. But pressure difference of the caused by the flow, airflow, is such that leads to bending and results in generating of the bending stress of the blade, level of which the bending stress even greater than level of the stresses caused by centrifugal force. And this is about what we can say about the compressor blade. And what we can say about the turbine blade. The same situation with the turbine blade, but due to much higher thickness and due to the much higher density of material, the turbine blade is heavier and stresses caused by centrifugal force in the turbine blade is higher. This is why the bending caused by the gases loading is less, and so relation between bending stress and tension stress is different for the turbine blade than for the compressor blade. But in addition to the acting of the centrifugal force, to the acting of the flow, like pressure difference caused by the flow, the turbine blades are additionally loaded by the high temperature, by temperature difference due to the temperature of the flow is not uniform along the blade length, blade height. The flow temperature is not uniform, and this will lead to non-uniform heating of the blade. And the reason of the thermal stresses is not just a temperature, some level of temperature, high or low, doesn't matter. The reason of the thermal stresses that appears in the any component, in the blades, turbine blades, in the disc, turbine disc, and disc of the compressor, last stage of the compressor. The reason of the thermal stresses is the temperature difference, thermal gradient in the component, in structural component, because of non-uniform heating. non-uniform, in result non-uniform temperature distribution in the material, we have the different thermal expansion in different areas or different zones of the same part, same component. And this leads to generating of additional deformation, additional hidden strain, thermal strain, and corresponding thermal stresses. What we can say, so this is about what we can say about the operational conditions. Operational conditions can be described by two different types of loading. Power loading caused by the pressure, forces, moments, and so on. And thermal loading caused by the temperature, which is different than the room temperature. So, if we describe some structure which operates under the room temperature, we can exclude the thermal state from the analysis. Well, and now let's try to explain, to understand what is the stress relaxation. Stress relaxation. So if we have the structural component which is operates under the conditions, under some, which is loaded by some type of loads, stress relaxation means what? Means the decreasing of the stress level during the operational time. But this decreasing of the stress level appears under the same load. The loading of the structure is not changed. It is constant, stays constant, and doesn't change. And moreover, the stress relaxation it is caused by the creep of material, by the elongation of the material, and by increasing in the plastic deformation. Increasing in the plastic deformation with time, but without changing in the load, So under the constant laws, the plastic deformation. What is the plastic deformation? I hope you know that deformation can be elastic and plastic. And creep of material, elongation of material, it corresponds with increasing of the plastic deformation with operational time. So it means that the loss is not fast loading. It means that the structure operates during long time. So again, we should take into account long-term strength or such issue like operation of the component under some given and constant conditions during the long time. And during the long operational time, which is measured by hours, by 10 and hundreds hours, or maybe more, 1,000 hours, the level of stress from time to time became lower. So level of stress decreases, and that is why we can say that we can detect the relaxation of stress. Relaxation means decreasing of the stress. But it is very important that the decreasing of stress appears under the long operational time, under the high temperature, high and constant temperature, and under the constant loading. The loads are not changed. Thermal loads and power loads are not changed. They stay constant. So operational conditions are constant, but they act on the described structure during the long time. And we can detect such situation like decreasing in the level of stress, like relaxation of the stress. And this caused due to the creep of the material. So what is creep? Creep is increasing of the plastic deformation in the material. And when the creep can appear, of course creep can appear if under the high temperature and under the long operational time, the level of stress, the initial level of stress that generated in the material will be greater than the yield strength. Do you remember what is yield strength? Yield strength, this is such level of stress if we will not exceed, if loss will not exceed, will not lead to exceeding the yield strength, how to say correctly, if loading is such that the level of stress will not exceed the yield strength. And when we will deactivate, when we will remove loading, deactivate loading on the part, the stress will disappear. And strain also will be disappears up to zero. So the size of the part of the structural component will take the initial value. But the plastic deformation cost or not cost appears, plastic deformation appears if the acting stress is greater than the yield strength. In this case, the deformation or strain can be described as a sum of two different types of strain. Elastic strain, elastic deformation, and plastic strain. And combination of them, sum of them, elastic plus plastic deformation. And creep appears only if we have in material the plastic deformation. So if the loss doesn't lead to appearance of plastic deformation in the material, creep will be not such property or such process in the material like creep will be not appears if level of stress, initial level of stress is not exceeds the yield strength. So to talk about the stress relaxation, we need to remember that first, the stress relaxation is possible only if the initial level of stress is greater than the yield strength. Or by another word, if we have the plastic deformation of the material caused by the loading. This is first point that must be present. Next point, the loading should act during the long time. This is second point. And the third point is what? Third point is next. The loading should be constant. Temperature should be high, like when we describe the long-term strength, it should be not less than approximately, again, for different materials. The critical level is different, but approximately not lower than 60% from the melting temperature. So it's high enough temperature. The structural component should be hot. So this is point number 3. Then point number 4, very, very important. The total deformation of the structure should be limited, rigidly limited. Should be total deformation, should be fixed. And in this case, due to acting of the same load under the same and high temperature, in material, we have the increasing of plastic deformation, plastic strain, plastic deformation, we start, and due to increasing of plastic deformation, the level of stress will be decreased with time. So the tension or tension, usually it caused under the tension. The creep is caused, is appears under the tension, or bending maybe. But bending also can be represented like a combination of tension from one side and compression from the opposite side of the bar. So under the compression, I am not sure. Maybe we cannot talk about the, but maybe yes, why not? Maybe yes. But primarily, when we talk about the creep, we talk about, we understand that we talk about the tension of the material or some load case which can be represented by tension. Well, uh, creep, or if creep corresponds or depends on the plastic deformation, plastic strain, let's look how does it change the level of plastic strain, how does it change during the time. Give me a moment, I will find the tutorial and share my screen. Well, let's continue. So this is the dependence of the plastic deformation, epsilon C plastic deformation or plastic strain, dependence on the operational time. So here is along horizontal axis here and here. This is the operational time or time to fracture. This one, time to fracture, which depends, time to fracture, you already know, by the previous topic, you already know the time to fracture depends on the level of stress and level of temperature for the same material. And so this is why it's function on the Aitken stress and Aitken temperature and corresponding plastic deformation. And you can see that the plastic deformation it increases with time, with operational time, and up to some value after which we have the fault of material. We have the destroying of the material, destroying of the structural component. And in general, so this is the common view, and you can see that this diagram corresponds with what? It corresponds, let me just a moment. Actually, it corresponds with temperature and stress that should be constant. Because if something will be different or not constant, we cannot already use such dependence, such relation between the elastic deformation and operational time. So this diagram is given for the constant temperature and stress during the loading of the structural component of the material. And this is a general view. If under the same temperature we will load the material greater, so if we will generate the higher level of stress, the diagram will go in another way. It will be changed. If under the same level of stress, we will change the temperature, increase or decrease temperature. Also, this diagram will look different. So it will be like a set of the curves, and each curve should be given or can be obtained only for the constant temperature and constant level of stress caused by the operational conditions. Well, general view of this diagram, of this curve can be approximately divided on three stages. Stage number 1 from the 0 to point A. Again, this is just approximately. Stage number 2 or zone A, B, and stage number 3, this is zone B, C, segment BC on the diagram. And let's describe what happens with in the different stages, what happens with the material. In the first stage, in the first stage, from the 0, which begins from 0, of course, 0 in the strain, in the stress, strain, in deformation, and 0 in time. This is just a new component, new part, which is only was manufactured but not loaded by any loss, thermal and power loss. And at the first stage, velocity, or how to explain, speed, not speed, velocity, creep velocity. So this is velocity of increasing in the elastic deformation. This velocity is decreases. So increasing in the plastic in plastic deformation, epsilon c, it is not constant and it is decreases. We can say that velocity of the increasing in plastic deformation or creep velocity decreases. Initially it can be high, and then with operational time, with increasing operational time, it decreases and finally gets some constant value. So here is stage number 2. You can see it has the same constant angle to the horizontal line. And it means that with increasing in time, we have the constant increasing in the plastic deformation, plastic strain. And this is stage number 2. And finally, stage number 3, again increasing, we can detect the extreme increasing in the creep velocity. So with with small increase in time, we have the high increase in the plastic deformation. It just can be explained by the increasing in the creep velocity. And why it happens, why it looks so. The first, the second, and third stage in the creep process. Okay, let's try to understand. At the first stage, we can obtain after the part was manufactured, we can get some hidden defects in the part, in the structure of the material. I mean defects in the on micro level, not in macro level. It's not some crack or I don't know some porosity in the material. No, it's big enough defect. But in micro level, in structure of the crystallic grid, some defects can appear, and after due to the manufacturing process is not idle, and these defects will lead to high creep velocity. But these defects will be under the loading. They will be maybe how to say, will be closed or will be moved outside or will lead to loading. External loading can lead to changing in the number of level or size of these internal defects in material, and can lead to moving of these defects, like to make changes, can lead to some changes again in micro level in the material structure, and the elastic deformation, the velocity of increasing in elastic deformation will be decreases. So, and this is the first stage in the operation of the part. Like during the testing, during the first loading by the maybe first loading of the part by the operational conditions, and so on. And then we have stage number two. Stage number two, this is normal operation. Normal operation, and the material operates as usually, nothing happens with it, nothing happens, in micro level. So when we describe the creep, we should describe the defects in micro level, in crystallic grid of the material. And nothing happens with the material, and it operates normally, and we have the constant velocity of the creep, constant increasing in the plastic deformation. But after some time, after some operational time, after point B, the changes, material, how to say, we get such situations where the changes in the material structure are initiated, and the number of internal hidden defects in the material structure, micro defects in the material structure, begin to increase. They increases the old defects which were appears during the technological process. They begin to increase, so they grow, and the new defect appears, and due to this situation, the plastic deformation increases, so creep velocity increases, and with each next loading, each next operation, the plastic deformation increases higher or faster and faster, increases more and more and more. So increasing in totally increasing of the plastic deformation with time became faster and faster. Velocity of the creep increases, and it finally leads to the broken of the material, to the fall of the material. So, and point C corresponds with fracture, with material fracture, and this is why at the point C we have the time to fracture, which we have described when we studied the previous topic, long-term strength. So long-term strength corresponds with this point in such diagram. Time to fracture and corresponding level of stress which can be, under which material can operate. So this will be, but here is the strain. But this is strain that corresponds with some level of stress, and this is time to fracture. I hope it is clear a little bit. Another diagram, another figure, and this diagram, let's say a few words about it. Material, depending on the type of material, it can be different. For example, we can detect 3 stages in the creep velocity, in the increasing or changing of the level of elastic deformation, like we have described on the left figure. So here is the curve that corresponds with sigma 2. We can also detect such material, or if level of stress is very high, the stage number 2 and stage number 3 will not appear. Only stage number 1 and broken of the material, the fracture of the material, and that's all because of very high speed, very high velocity of increasing of the elastic deformation. And stage number 2 will even not appear. So, or some type of material can has such a behavior like absence of the stable creep of velocity, constant creep of velocity, stage number 2, and especially stage number 3. or or some other type of material also can be detected, in which we have only stage number 1 decreasing in the velocity of creep, and then like a normal operation stage number 2, but this normal operation like a fault of material appears without increasing in the velocity of creep, without stage number 3. It's just a normal operation and sudden broken, sudden fault of the material, sudden fracture of the material. Such type of materials, such a behavior of some materials also are present. But more common state, this is intermediate Q here that represents all 3 stages, presence of all 3 stages. The first one, decreasing in the creep velocity. The second one, normal operation with constant creep velocity. And the third one is the growing of creep velocity, increasing creep velocity, which leads to the dramatic increasing in the elastic strain and results in the fracture of the material, fracture of the described component. Well, this is like what is the creep, and moreover, I forgot to say the creep appears only if the total deformation. So we talk about what? We talk only about the plastic deformation. But we forgot about elastic deformation. The total deformation can be described as assumed plastic deformation plus elastic deformation. Plastic plus elastic. And the total deformation should be limited. In this case, we can talk about not creep, but we can talk about relaxation of the stress. Relaxation of the stress. What does mean the total deformation of the structure is limited? For example, let's describe flange and bolt connections. Flange and bolt connection. Two flanges are tightened. So two flanges are tightened by bolt. Yeah. Let me take something. We have a flange which is tightened by bolt, and these flanges first, the bolt will be tensed due to tightening, and then the two flanges maybe or not two flanges. Okay, let's describe such situation when flanges we have not loading of the flanges by the axial force, which try to lead to opening of the gap between flanges. So no axial force acts on the flanges. Only we have the tightening of the bolt just to ensure the tight connection of the flanges and absence of the gap between them. Okay, let's describe situation that due to tightening of the bolt, we have the plastic deformation in the bolt, plastic deformation in the bolt. And moreover, we have the acting of the high temperature on this whole structure. So it is not only default, it's not has only the plastic deformation, but it also has the high temperature. And under the high temperature, the level of total level of deformation will be constant because we don't apply tension to the flanges. We don't push them outside. Okay? Okay. Only plastic deformation due to tightening of the bolts and plastic deformation in bolt. And under the high temperature, the bolts doesn't change. Only 18 of the high temperature. And under the high temperature, in the bolts, the amount of plastic deformation will be grows. It's not fast process. It's measured by hours, by 100 hours. So it's not a fast process. But the level of plastic deformation will be increased with some constant, constant velocity. This is the creep in the material. And the total deformation described by what? By the distance between flanges, between left and right wall of the flanges. The flanges, total thickness of the flanges is not changed. It is constant, stays constant, because we don't apply tension to the flanges. But due to the high temperature and due to the initial plastic deformation caused by the tension in the bolt, the plastic deformation in bolt will be increases, and but total deformation will be it is fixed by the operational conditions, and elastic deformation and plastic deformation. So elastic deformation will be decreased if total is constant. The amount of plastic deformation increases and plastic deformation decreases. And the stress will be also decreases because it's like how to explain? It's because of decreasing of the plastic deformation in the bolt, the stress will be decreases. I hope that you will describe this issue together with Professor Pifanov in more details of the lecture, and let me show how to calculate, how to simulate the such issue like relaxation of the stress caused by the creep. So creep can be simulated, can be described again by some model, and model which we can use for describing such curve. This is the Norton model. And Norton model describes only the second stage of the creep process. Only second stage, stage number 2, with the constant velocity of the creep. This is the curves of the creep represented in the relative time, like actual time divided on time to fraction. And in this case, the axis, horizontal axis, will be changed from 0 to 1, because 1 it is situation when the actual time equal to time to fraction. And in this case, all of the curves for the given material and for the given temperature can be combined in single curve. Like for example, you can see here for the some material, some example. This is what for the 900 degree this curve, this dependence of plastic deformation on the temperature for the relative temperature, for the relative time, sorry. For another temperature and for the another temperature. So the greater temperature, the low plastic fracture appears under the low plastic deformation. You can see here. So time to fracture here is when it is 1. So it means that we have a fracture of the material, we have the fault of the material, and if material operates under the lower temperature, level of plastic strain is greater. But if we provide heating, if we heating more intensely the material, so the fracture appears under the lower level of the plastic deformation. I think it's clear. Creep velocity is described like d epsilon by dt. Epsilon is the plastic deformation, epsilon c, and dt, this is time. So derivative of the deformation, plastic deformation by time. And the Norton model you can see here. Norton model set correspondence between creep velocity, we see creep velocity, and actual stress in the material under the constant temperature. So this is B, this is parameter, like a coefficient, parameter of the Norton model, and over this parameter, and also this is parameter of the Norton model that depends on the temperature, depends on material and temperature, and they are, this B and N, they are constant if temperature is constant. So, using this assumption that parameters B and N are constant if temperature is constant, we can find the creep velocity for the given material using the curves of the creep. And usually the creep velocity is measured or takes values in range from 10 e minus 5 to 10 e minus 3. In percent per hour. Well, relaxation of the level of stress can be described. So if we will apply the Norton model, from that model we can find the changes in the stress. This one, changes in stress with time. Here is sigma 0. This is initial stress caused by the actual loading conditions. M is what? M is parameter of the Norton model. This one. Alpha 0 is calculated according to this equation, where E is elasticity modulus, M and B parameters of the Norton model. sigma 0, again, this is the initial stress generated by the loading conditions. And here is in this equation, T, this one, this is operational time. So, with increasing in time, we will get decreasing of the level of stress. We will get the relaxation of stress. And your task will be find stress relaxation, find the parameters of the, let me show this equation, find the parameters of the Norton model, this one, B and N for the given material and for the given operational conditions according to the variant. And when you will find the parameters of the Norton model, so first you should find the creep velocity. By creep velocity, you can find the parameters of the Norton model. And then, when you already know the parameters of the Norton model, you can find the relaxation of stress with time. How to do it? It is explained in the explained by this formula and explained in the task. Again, like for the first one, I will translate it and share it with you. Now it is not translated, so now here is just a variance. Variance 1, 2, 3, 4, 5, and so on up to 9. You have the variance, I already provided to you the variance. Let me find where it is. Practical works, variance for practical activities on lifetime and cut in a year. Lifetime, let's open this file. I have shared it with you in WeChat. And lifetime, variance 1, 3, this is for practical activity on practical activity number 1. Here, I will add the practical activity number 2 and variance that I will give you will be here from this table. So I will translate this tutorial, not all of the tutorial, without theory, because theory you will describe on the lectures together with Professor Epifanov in details, in more details, and you can use the lectures notes for studying this material by yourself. I will translate only the order of the calculation with variance and so on. So beginning from here, characteristics of the material properties. This is Larson-Miller model. Similar for all variants for this practical activity, and also depending on the variant, in variant the temperature will be given this or this. Let's look here. The temperature, what is given in the variant? The acting temperature 900, 900, 900. 950, 975. And the level of the stress, actual stress, this, you will have one from fixed variance. And depending on this, from this table, you should take the epsilon C and the relative time. So, from here, from this table, relative time you get, okay, then you will need to recalculate the relative time, this one, this column, recalculate it in the time in hours. How to recalculate? You should use this model, Larson-Miller model, for the given material and calculate time to fracture. First, time to fracture, because relative time is what? Let's find this equation. What is the relative time? Here is relative time. This is the actual time divided on time to fracture, which depends on the stress and temperature. Stress and temperature you have in variable. So by stress and temperature, applying Larson-Miller model, you can calculate time to fracture, and then by the relative time and time to fracture, you can find a time in hours. So it will be necessary to rebuild, not this one, rebuild or recalculate the relative time given in the hours by the time to fracture, which depends on temperature and level of stress. And to calculate time to fracture, you should use this Larson-Miller model, this one. And then here it will be given in step by step, it will be explained what exactly and how should you do. So this is it. It was this one and this one. This is all of this. This is initial data. This is the initial data. And model elasticity under the temperatures 950, 975 is 1.3 multiplied by 10 in power 5. Okay. Well, so here is given the order of the calculations. What exactly should you do? I will translate it and provide it to you for calculations. So, and then again, like the first topic, like the previous task, previous topic, you also should perform calculations in form of such table. Just put here from your variable, put here your relative time, epsilon c, just replace here from table 2 to epsilon c. This is it. According to the temperature from the variable, just put here the same values. And then calculate time in hour, just like relative multiplied by time to fracture. And time touched, also how to calculate it will be given here, explained here. Well, and then calculating the parameters of Norton model. Also, I will put here the equation by which should you calculate equation 213, 214. I will add it here and give you translation and report on the work and questions for self-control, self-study and self-control questions. So that's all. I will not show how to perform calculations right now. Maybe I will do it and make a short record, short video. But first, I will translate this part and provide it to you that you can start to calculate this topic. From my side, that's all. For now, that's all. Wait for translation of this part of the tutorial. I will try to provide it to you up to Monday.